Hello, ladies and gentlemen. This is lecture number 5 on practical numerical methods for PDEs. The topic is specifically adaptive mesh refinement and the according algorithms. So with lecture 5, we are actually getting where I want to be with the material in this lecture. The previous couple ones were necessary as introduction, but now we'll do fairly specific concepts, algorithms that some of you have not seen before and that are nevertheless really useful in practice, especially in large-scale high-performance computing. So let's look at the slides. Section 3 is tree-based adaptive mesh refinement. We had some introduction to this earlier in section 1. The question, of course, is why would you have adaptivity in the first place? And I talked this over earlier today in our group session. So the essence is that with uniform refinement, you're wasting performance if this high refinement is not always needed or not in all places, in all locations of the simulation. So if we have localized features, we may want to restrict the very fine elements to this area of interest and keep the other elements coarse. I will not talk about high order methods here. They are a viable option for many applications. In our case, we will concentrate on H adaptivity, also known as local element refinement. So if you look at this picture here, we have two sorts of element refinement. You see that there is a coarse region in the mesh here or here, and there's a fine region over here and over here. And in the left-hand example, this has been achieved by so-called conforming refinement. We see that two elements always share a whole face or no face at all. For non-conforming refinement, you see that this big element on the left shares one face with multiple elements, and those elements only share part of this bigger face. Both are viable options. You see that the right-hand side picture allows for a hierarchy or a recursive interpretation, while the left side picture does not. And so we will concentrate on the non-conforming style for the remainder of this lecture. Adaptivity in general has advantages as motivated earlier, especially if the solution has localized features. There are cases when adaptivity is not required or not warranted, for example, when the solution is equally smooth elsewhere. So in this case, to still be able to use adaptive mesh technology, that technology needs to be so fast that it does not really matter if you use it or not, in terms of the rest of the simulation being a lot more expensive than the part that we need for adaptivity. So in this sense, we are interested in really, really fast, efficient, and scalable methods. Scalable means that we can enlarge the problem size without the adaptivity runtime growing out of proportion. And my proposition is this is all very possible and very real. And my opinion is that the methods shown in the remainder of this lecture are exactly what is the recommended way if those are your goals. So to review the tree-based idea, you can consider multiple different ways of identifying a mesh that is refined with a tree. Both of those histories here from left to right with the non-conforming triangles or the non-conforming quadrilaterals are both equivalent in the sense to this one tree. And there is interest in working on this triangle method as well. I've done this before together with a graduate student of mine who's really successful applying these techniques. But I will here concentrate on the bottom row, the squares and cubes in 2D and 3D. Excuse me. So I had previously introduced lexicographic ordering. Historically, this method has a name. It's called the Morton order, which was developed in 1966 for a two-dimensional geographic information code. Basically, And this is a concept that's extendable to arbitrary space dimension. It is also called the Z order. Why? Because the lexicographic ordering in 2D leads to a Z-shaped path through the various children. And recursive refinement is defined by a refinement rule, which specifies for a given element how many children will there be for this element. In most methods, the number of children is the same for each element, but there are methods thinkable where this is not the case. And the relative order and position of these children with respect to the parent, which again may depend on the element for different kinds of curves, such as the Hilbert curve, for example, that I'm not covering here. So in 2 dimensions, you see it is lower left, lower right, top left, top right. In 3 dimensions, we do this once on the bottom plane, and then we do it again on the top plane, which leads to this z-curve on the bottom, and then another z-curve on top of it. With the proper numbering of children, the number of children is 2 to the power of d, the space dimension, so it's 4 in 2D and 8 in 3D. We had proposed earlier to restrict the method to some maximum level big L. For practical purposes, L can be as large as you want. We then have a cube of coordinates with one coordinate for each dimension, and that coordinate is an integer that goes from 0 to 2 to the power of big L exclusive. So this coordinate refers to the lower left corner of an element with respect to that coordinate cube that is, of course, meant to represent the unit cube in the simulation domain. So if you can just pick any arbitrary set of coordinates and an arbitrary level, is it guaranteed that this will be a valid element? No. Valid are elements that are derived by the refinement rule recursively, beginning with the root, picking one of the defined and possible children, and do this recursively for each of those until you reach a certain level. So each child operation increases the level by 1, so there is only a unique way to creating any element. So we had introduced the isvalid function a couple of weeks ago. Basically, it means that the rightmost bits in binary representation, which I will allude to constantly from now on. So the size of the element in this coordinate cube is 2 to the power of big L minus little l being the level of that element. So what does it mean? If the element is the root, that means little l is 0. We have a length of the element 2 to the power of L that is equal to the length of the cube, which is exactly what the root is supposed to be like. For, say, the smallest possible child, where little l is the same as big L, we have 2 to the power of 0, which is 1. So the smallest possible element at the maximum level has in integer coordinates just a size of 1 unit. And everything in between is possible by powers of 2. Valid elements, if you look at formula 142, are those where the rightmost big L minus little l bits are all 0, which means that the element coordinate is an integer multiple of its length. So you can only arrange the elements in steps that are multiples of its length and not somewhere in between, which makes perfect sense, I hope. So the Morton refinement rule translates into a specific child algorithm. The child is defined by the rule, and if we understand the Morton rule as using lexicographic refinement between all the children of some element, then if some element is defined by the coordinate tuple vector x here and its level, then there can be 2 to the power of d children, and any one of them indexed by j can be created. So j would be anything between 0 and 2 to the power of d exclusive. And what we do is for each coordinate direction separately indexed by little I, we either take the lower left corner of the element, and if it's an even index in that direction, we keep it there, and if it's an odd index, we move it one step to the right by the length of each child, which is no longer h, but h over 2. So if if you see this bitwise AND operation. So if the ith bit of j is between 0 and 7 in 3D, so it has a bitwise representation between 0, 0, 0 and 1, 1, 1. So it has one position for each dimension, and with this AND operator we just check if in dimension I there's a 0 or a 1 in this number. And if it's a 0 we take the left bottom front, and if it's a 1 we take the right top and back. And the level of course goes up by 1, so this defines a child, and the parent is just the inverse. If we go down to any of the children, they will all have the same parent, namely the original element. And so you see if we go down to a child, any of the legal j values, and then we take the parent again, we end up with the, oh sorry, this should be x comma l, the element with the level. Likewise here it should be x comma l, excuse me, in this script. If we take a parent of some element first, which we can only do if the level is not the root, right? So if L is strictly bigger than 0, we can take the parent, and then we can go to any of the children, and we may arrive at a different element, at a sibling basically, or at the element itself, depending on j. So j has to be a specific number to reach the original element again after doing the parent and the child, and that number is uniquely defined by this element. We call it the child ID. So how would we understand what is the proper number j that satisfies this equation for any given x and l? So the child ID is the number of a child relative to all of its siblings. We can compute this separately, just given some element, any element with a valid pair of coordinate and level. And then we would basically check again the bit of the coordinate corresponds to the length of the element. So if the element is an even multiple of its length in this position, we get a 0 result, and if it's an odd multiple of h in this coordinate direction, we get a 1. So this comparison gives us 1 or 0, in this case actually multiplied by some power of 2, that is h. So the result of this is either 0 or h. So we just take the yes or no here and multiply with what? With 0 for x, 1 for y, and 2 for the z direction. So basically we construct a 3-bit number, I going from 0 to d minus 1, which is a number in the proper range between 0 and 2 to the power of d exclusive, which is the exact correct input of j for this function up here. I hope this makes sense. It may not in the beginning, so please go through a couple examples. Take a piece of paper, draw the root, pick a child number, compute the coordinates, pick big L to be anything you like, 3, 4, or 20, and then work through several of those algorithms, child-parent examples, until you really understand what the bitwise implications are here for the coordinates. So write down the coordinates always as binary numbers, and see if all of this makes sense to you. Especially h, the length, is a power of 2 by definition. So a power of 2 in a binary system is just the number of all zeros with one position being 1. And that position, in this case for h, is big L minus little l counted from the right. So we could now write down what the parent function actually is. We can create it by basically, what do we do if we have a child and want to turn it into a parent? It could be that we can just keep the coordinate. If the child and the parent have the same lower left coordinate, we would keep x in this direction. But if the child is, say, to the right or to the top of the parent coordinate, we have to actually reduce the coordinate by this h/2 amount, that it is further advanced in space than the parent. So the way we do this is just zero out the bit that is at the position of the child that would not be compatible with being 1 in the parent. So if you look at the isvalid function, we want the parent to be a valid element. If a parent is level L minus 1, then the h bit of the child must not be set in any of the coordinates. So the way we do this is creating the bitwise AND of this power of 2. If a power of 2 has just one position 1 and the rest zeros, the bitwise negation of this has this position 0 and all other positions 1. So if we do the bitwise AND, that means the 1 positions in the other operand will not change, but just this one position, big L minus little l, will be 0, which means the corresponding position in the coordinate in that direction will be set to 0. Again, please make several examples on paper to be very sure that you understand what's happening here. If you have some handle on these operations, the question arises, of course, if there's an if and only if connection between valid elements and those elements that are obtained by recursive refinement. I'll just prove one direction here. The statement is that any element derived from the root by refinement, that is by the child function recursively, is valid by formula 142. So how would we prove this? This is an induction. We begin with the level little l being 0, which is the root. So we just have to figure out if the root itself is valid. And this is the case, since the root has 0 coordinates in the lower left corner. So the isvalid check in that equation is trivially satisfied. So the step of the induction now is to assume any valid element of level L. And then apply the child function to this element. This means actually if xl is valid, that means the rightmost big L minus little l bits of every coordinate are 0 by induction assumption. So the child function will then possibly add another bit to be 1, and that is the bit described by h/2, which is the length of the child. If you express this, it is 2 to the power big L minus L plus 1. And this is the first bit that is to the right of the previously 0 bits. This is suppose the parent has a certain set of bits that may be 0 or 1 legally, and then to the right, on the screen it's the other way around, right? So the right would be here. Those would be all the 0 bits, the least significant ones. And then h/2 is exactly the last one of all these 0 bits for the parent that for the child actually would be legal to be 1, which you can look at. So in x here, the input x, we know that the h/2 bit is necessarily 0, and if by the child function we add h/2, we can only change this bit to 1, or we will not, depending on the j, the child index, that goes into the child function. Any j will be valid here, which means that the next bit over will possibly turn from 0 to 1. But on the child, we have one less bit on the right that has to be 0. So we are filling exactly the bit that in the parent has to be 0, but in the child no longer has to be 0. So the result is valid, which completes the step of the induction. And we're done with this proof. So since we already looked at a couple of videos earlier today, this will be enough material for this week, especially considering that I find it very much recommended to really take a piece of paper and spend half an hour going through a whole bunch of examples in 2D and 3D, maybe in 1D if you like first, with various big L's, and just run the child, the parent, the isvalid functions bit by bit, number by number, until you really get this idea. As always, if you find any errors or things that do not make sense, please write me an email. Don't wait until next week. And I hope you can enjoy this construction. We will advance a little more next week on further relations between elements across multiple levels. Right here we just have considered direct parent-child relations, but of course you can have multiple levels in between two elements of disparate sizes then. So we can look into ancestors, ancestor IDs, and we will also count elements with respect to the finest mesh, which gives us a linear ID and maybe one or two more element local functions, basically transformations from one element into the other, before we go into global algorithms where we look at the whole mesh, which is a list of all leaves of the tree. And each of these leaves is one of those pairs, little x and L. So enjoy working through all this, and I see everybody on Monday next week. Thanks.